Assalamu alaikum warahmatullah. In the interesting subject of the world, physics, we are going to discuss a beautiful topic. It is force on a current carrying conductor placed in magnetic field. It belongs to the unit magnetic effects of current and magnetism of standard 12th. Okay, here is the diagram shown for the topic. See, it's a conductor through which current I is flowing. This conductor is placed in a magnetic field B. Let theta is the angle between the direction of this conductor and direction of magnetic field. Okay, so let us write down some related points regarding the topic. Yes, here it is. I is electric current flowing through the conductor. N is the number of free electrons per unit volume. Since there are the free electrons, let small n denotes the number of free electrons per unit volume of the conductor. Okay, Vd is the drift velocity of the electrons. Whenever electrons are placed in the electric field, they get drifted, which we call as drift velocity. Okay, theta is the angle over here. A is the area of cross section of the conductor, right? Now we know whenever a charged particle is placed in magnetic field, it experiences a force. Let us take first the single electron. Here the single free electron, as it is in when the charged particle is placed in magnetic field, it experiences the force. Okay, let us take the single electron, okay, place it in this magnetic field, and we are going to calculate, we are going to write down the relation of the force for this single electron. Okay, that relation we know is generally given as F is equal to Q, means the charge, and V cross B. V is the velocity of this charged particle and B is the applied magnetic field. For electron, this charge will be given by minus E, and velocity of it is here the drift velocity, and B is applied magnetic field. So the force experienced by this free electron, by the single free electron, is given by this relation, right? See, this force we discussed for the single free electron. Okay, single free electron in this conductor. Now let us take a length of this conductor, a small length having dl as the value of its length. Let us take and calculate the force experienced by this small part, by the charges of this small part. Okay, now consider a small current element of length dl, this small dl of this conductor. Then in order to calculate the force, first we have to see how much free electrons are present in this small element of length dl. Okay, in order to calculate the number of electrons in it, first we see what is its volume. Okay, then we multiply it the number with the number of electrons per unit volume. By that we can get the total number of free electrons in it, and then we have to multiply the total charge of the single electron in order to get the total free charge present in this small unit. Here it is. Now consider a small current element of length dl of this conductor. Then the volume of this element, volume we know it is area into length, meaning area of cross section into it is length, right? This is the volume of this small portion, right? Volume of this small portion which is shaded over here. Okay, then when we multiply it by small n, we get total number of free electrons in this current element, right? Because n means the total number of free electrons per unit volume. Okay, by multiplying it to this volume, we will get the total free charge in this small volume, right? Then multiplying the charge of the single electron, we will get the total charge present in this small element dl. I have written here. So total charge in this element, that is represented by Q, is equal to the whole of these number of electrons into the charge of the single electron E. Okay, so it is minus E Na dl. This thing is multiplied by minus E, the charge of single electron, to get the total charge present in this small portion dl. Okay, see here it is. Now we got the charge in this small portion. By using this relation, again we will get the force experienced by this small part dl, right? I have written here, hence force experienced by this current element is given by it is df. Here it is force, the general relation for force F is equal to Q into V cross B. F, I have replaced it here by df. Okay, it is not any big difference. Okay, so df denotes the small force by this small element. Okay, here this portion ENADL, it represents the charge. Here it is Q, and VD is simply the velocity, and B is applied moment. So this relation and this relation, they are one of the same. These relations, only the difference is here the charge is represented by Q, and here the total charge value is this. Okay, so this is the force experienced by small element of this conductor of length dl. Okay, now we have to calculate the total force of whole experienced by whole of this conductor. Simply we know this force we can get simply by integration. So let's proceed. Yes, here it is. Total force experienced by whole conductor is given by integration. Integrating the previous relation, that is the relation number 3. This is the integral sign to get the total force by whole of the conductor. This is the relation. Now let us insert the new relation. We know the relation for drift velocity is dl by dt, meaning the length covered, distance covered by the charge, and what is the time in which it covers the given distance. And this negative sign shows that the direction of this current and conductor, they are opposite. Okay, using this equation 5 over here in here Vd, right? This we get df is equal to this thing, and then this Vd, it will get replaced by dl by dt. Here Vd gets replaced by dl and divided by dt, it is here dt, right? Then this term, this above numerator in this relation ENADL, it represents the total charge present in the small element dl, right? Here I have written, so this can be replaced by dq. We get this dq over dt, and then we know that the charge per unit time, it gives us the electric current I. Okay, so now let us integrate it to get whole of the force experienced by whole of the conductor. Here I have written only, but I have not integrated it. Here I am going to integrate it. This df, it comes to be f, and here only the variable is the length. Okay, here this dl gets converted into l, so we get this relation, because a cross b, we know it is equal to ab sine theta. Here comes sine theta, right? Now if angle is 90 degree, it is the angle, let me bring it here. This, if I will keep this conductor by this in the direction as given by the pen, then the angle of this pen, meaning the conductor, and this magnetic field, they make us 90 degree angle. Okay, here, so if angle is 90 degree, then this we know sine 90 is equal to 1, right? I have written here an interesting fact. This is the force which is experienced by the conductor, by this conductor. This force then experiences the force. Okay, that force is given by the relation F is equal to IBL. Okay, so in order to have the direction of this force, we use Fleming's left hand rule. Let me show you by this. If this is my left hand, this let me indicate Fleming's left hand rule. See here, if this finger, it denotes direction of magnetic field like this. Let me show you like this. These are the B lines, meaning this finger, middle finger, it denotes direction of magnetic field. Let me keep the conductor like this, meaning since we know that through the conductor current is flowing, so this in other words denotes direction of conductor, direction of electric current. This is the direction of current, meaning they are at 90 degree. Then by Fleming's left hand rule, if we keep our thumb mutually perpendicular to these mutually perpendicular fingers, right, we will get the direction of the force, right? So these two are, if this finger and this finger denotes magnetic field, this denotes direction of conductor or direction of current, they lie at plane of the paper. Then the force experienced by the conductor will be perpendicular to this plane, meaning the plane of the paper and outwards. okay, outwards. That is the conduct. If this is the conductor at 90 degree to the magnetic field, then by applying the current through it, this conductor, it will experience a force outwards like this. It will come upwards at 90 degree, okay, at 90 degree outwards to the plane of the paper. So this is the general relation given by the force experienced by it, and this left hand thumb rule, it explains us the force experienced by it when the magnetic field direction and direction of current, they are mutually perpendicular to each other. Then this thumb remaining perpendicular to both of these two will give direction of the force experienced by the conductor. So this was an interesting relation for the given topic. I hope you would have got it. Thank you. Have a nice day. Assalamu alaikum.